Hi everyone and welcome to this first video on the antiderivatives in the Year 12 Specialist Maths course. In this series of videos I'm going to go over some of the advanced techniques that are used for integration, and so we're going to start off today with looking at antiderivatives involving inverse circular functions. In order to do these questions we need to already be familiar with the derivative of the inverse circular function, so knowing that when we differentiate the inverse sine function we end up with this rule just here, the 1 over square root of a squared take x squared. And we need to also be familiar with the derivative of the inverse cos function that we can see here, or the derivative of the inverse tan function that we can see here. So if we are already familiar with those, then we know that when we anti-differentiate them, we're just going to go back to the original inverse sine, cos, or tan function that we had. So I'm just going to basically jump straight into these questions. So evaluate the following integrals. Something I will say actually before I go getting stuck into them is notice that the difference between the antiderivatives that give inverse sine or inverse cos, the only difference there is whether it's a positive or negative sign. So what I'd say is you can basically decide on whether you get an inverse sine or inverse cos, and change the answer to be whatever you want it to be, because we can just multiply by a constant and it doesn't really change our answer. So yeah, I'd say that most of the questions that you see in the book will probably give inverse sine as the rule, and just because it tends to be, I don't know, a bit nicer, I guess. So evaluate these integrals here. Well, looking at the first one, it is very much looking like the inverse, the derivative of the inverse sine function. So when we anti-differentiate, we're going to go back to get an inverse sine function. Notice that this number here is just the a squared that we see up here. So I know that a must be 4, and so then I can just substitute basically straight into the rule and get the inverse sine of x over 4, and then always remembering to have a plus c when we anti-differentiate these indefinite integrals. So the second question, I better finish writing that properly. Can't forget the dx. Again, it's looking like it's going to be an inverse sine. I'm noticing that there's a problem though, because I've got a 9 in front of the x squared. So I'm going to have to do something about that. I'm going to have to move that out of the square root function there. So to begin with, I'm just going to get this into a form which is a bit more favorable, I guess you could say. So if I take the 9 out as a common factor, I'm going to be left with 25 on 9 minus x squared in the denominator there. But when I take the 9 out as a common factor, it's only going to actually take 3 out the front of that square root sign. Still have my dx there. So I've now got this into a form which is a bit nicer. To perhaps make it even better, I could just move the 1/3, getting the 1 from here and the 3 from here. So 1/3 out the front of the integral of 1 over the square root of 25 on 9 minus x squared dx. And so that looks pretty good. That means that a squared must be 25 on 9, so that means that a must just be 5 on 3. And so when I anti-differentiate, I'm going to get 1/3 of the inverse sine of x on 5/3, and then plus c, which I can write that a little bit nicer and make the final answer 1/3 inverse sine of 3x on 5, and then plus c, and that would be the final answer. As for the third example, we're now dealing with a definite integral, and this one is looking like it's in the same form as the tan function. So it's a squared plus x squared in the denominator. Also notice that this one is in terms of t, so we have to anti-differentiate with respect to t, as this dt here tells us. And so looking at this, I can straight away see that the a squared is just going to be 9, just comparing it back to the original rule there. The other problem though is that I need a to be 3, and a is in the numerator there, so I need to have a 3 in the numerator. So to do that, what I'm going to do is set up the definite integral like this. I'm going to make that a 3. But I can't just make that 3. I have to also do something to counter that, so I haven't really changed the equation. So to counter the 3, I'm also going to put a 1/3 out the front. So 1/3 and a 3 just cancel each other out, but now I've got something that can actually be solved. And so this works out to be 1/3 of the inverse tan of t on 3, and then plus c. However, this is also a definite integral, and so this is going to be between 0 and √3. So when we do definite integrals like this, the plus c basically gets cancelled out in the process. All I'm going to do is sub the √3 into the equation first, and then sub the 0 into the equation second, and subtract the second result from the first. So it's going to be 1/3 of the inverse tan of √3 on 3. So that's one of the exact values, hopefully you recognize, and then minus 1/3 of the inverse tan of 0. And again, you can imagine if I had a plus c written here and a plus c written here with these in brackets, then the plus c's would cancel each other out. So the inverse tan of √3 on 3 should be just pi on 6. And so I've got 1/3 of pi on 6, which is pi on 18, minus, and then inverse tan of 0 should be 0. So I am actually just left with pi on 18 as the final answer. Anyway, that'll do it for the first video. So I'll leave it there and see you in the next one.